Hello. First, thank the organizers for the kind invitation and also the powerful push for my visa to the to the Tel Aviv embassy. I will talk about magnetic topological materials. It's mainly about topological Weyl semimetal. First, thank previous talk. Titus give a quite good overview about the contribution of Alexei. And actually, in my talk, you will recognize actually his legacy is everywhere. You cannot avoid this name. And to some sense, I think as a scientist, the name will continue as long as the work influence. First, I think the talk I talked with is collaborate. May I have the laser pointer? Yeah, I even don't know what it is. Wow. Well, let's go this way. And this work is collaborated with my former PhD student, Yang Zhang, and also my current postdoc, Yayun Ko, and Tobias Holder. And this work is closely collaborated with Fernando, who might be in the audience today, and also with Claudia and Nagosa. And Titus already gave a great introduction. Now here, I just want to repeat this topology briefly with this toy. And in reality, we classify the geometry by the shape. And then this idea was borrowed to understand the band structure of material. And if we have here, I use these groups to represent a band structure. If we make a topological change, for example, we switch the order between the valence and the convex band. The consequences on the surface, we will have metallic surface states. This represents an insulator. We have a gap separated by the firm energy. And then, when this is this idea proposed in 2D, then generate to 3D. 3D case, we will have a 3D metallic surface states. This is called bulk boundary condition. And we have something topological change in the bulk. We think the consequence on the surface is usually a surface state with this Dirac cone-like dispersion. We can also make another topological change in the bulk. Is, for example, we make a cross for the bulk bands. Similar consequences, we will have surface states. And then today, this idea is generalized to many different topological fields. Different name, topological Weyl semimetal, Dirac semimetal, nodal line, and even triply degenerate bands, and also like a higher order TI. There are many different fields, and in some sense, actually, I like these ideas even more is because these concepts has been realized in many materials already, and these material, they are not specially created for this topological fields. They are known material in the database, maybe for half century and even more. And then we use this topological idea to re-understand the band structure, and indeed discover many of these topological fields. And possibly next talk, Xiangang Wang will tell us actually today, after a high throughput calculation about the all known inorganic materials, actually nearly half of them are topological. Topological appreciated in a different way, either insulator or metal. And next our focus is about this semi-metal phase, this crossing in the bulk. This is kind of three-dimensional Dirac cone or Weyl cone. And there's a unique feature is about its behavior as a monopole of the Berry curvature. And I don't have to repeat what is this Weyl equation. And then actually here, the Weyl here, you can see from this solution, this Weyl particle, the momentum and spin will be either parallel or anti-parallel. And if this is a real particle, we call this chirality, left-handed, right-handed chirality. But well, this concept is slightly different from chemistry. Chemistry chirality refers to the molecular structure. And about this chirality is the relation between the momentum and the spin of the particle. And then go to condensed matter, we know like when the band start to cross, actually near the crossing point, the Hamiltonian can be exactly written this way, k dot omega. You can think omega as a pseudo spin, as not exactly the real spin, and k is the crystal momentum, although not the real momentum. And here, actually, this omega, we can actually exactly understand it as the Berry curvature. Berry curvature is simply a property of the block wave function. And it has a very well-known consequence, is this anomalous velocity. we know from a band structure, the slope of the dispersion is the group velocity, and we use it to calculate the conductivity. And then the consequence of barrier curvature actually will contribute a correction. This is called this Latinger anomalous velocity. This, you see, is E cross omega. E is the electric field, and omega is this field, this barrier curvature. Barrier curvature play like a magnetic field. And because this E cross omega relation, this is a pseudo-magnetic field in momentum space. And then in 2011, Xianggang Wang and Ashwin and their and colleagues, they pointed out a very important insight is here. Okay, in the band, we have this crossing, we have this monopole structure. Then on the surface, thinking in a way like a topological insulator, we think of the surface. Actually, the surface, there are also surface states. There are surface states on top of a metal. And then these surface states, actually, they form a special Fermi arc on the surface. Instead of a closed loop, we only have part of the loop. Actually, this Fermi arc becomes a very powerful tool to really identify which material is a Weyl material, and as a most convincing signature. And yeah, in addition, a remark about what kind of material can be a Weyl semimetal. We also learned from Titus is that it requires break either time reversal or inversion symmetry, or we break both. And yeah, before go to the detail of the material, like I would say first, let's look at about this velocity, this barrier curvature is consequence. And let's revisit the textbook slightly. If we want to study the current, we count, this is the charge, Fermi occupation, and the velocity. This is the standard with semi-classical. We count that there's a particle flow with this velocity. We integrate everything in the momentum space. And when we apply electric field, there's an electric field. When we apply electric field, the standard way is, electric field first change the Fermi occupation. This is the Fermi surface shift we are familiar with. Then the second, give a correction to the velocity. Most of the time, actually, we don't put the correction to the velocity. But here, you see the correction is exactly this anomalous velocity related with the barrier curvature. And in the Ashcroft solid-state physics book, we don't have this term. And we have both of these two sides. The change of the Fermi surface is just in the relaxation time approximation. I just copy from the textbook and I add this term. Let's elaborate slightly. We put these four terms one by one. The first term, clearly, it is 0, because this is equilibrium. And then the second term, this is the normal conductivity. Is proportional to the velocity square and the relaxation time. And then we get another two term. This term is clearly, you see, this E cross omega. Clearly, because the cross relation, if electric field is along X, and then the consequence is we will get a Y direction, so Y or Z direction. We get a current. This is the Hall effect. Or in other words, this is the Hall effect purely from the band structure. Then today, we know this is the anomalous Hall effect. But usually, we threw away this high order term, the second order. But if we put it back, we get another Hall effect, just proportional to the electric field square. It's quadratic. Today we know this is called a nonlinear anomalous Hall. And here this sigma xx, we know sigma yx is equal to just the integration of the barrier curvature for all the occupied states. This is well established. And then the higher order term, actually, I just copy-paste from here, copied here. It's related with the barrier curvature still, for sure. And then also related to relaxation time. And this is interesting. If something related to relaxation time, the sigma xx, we know, related with scattering. And here, this part also related with relaxation time. Later, we will come back and revisit this nonlinear term. Let's first go with the anomalous Hall. Or, in other words, how this is related with this Weyl semimetal. And we know by this formula, we integrate the barrier curvature, we have the anomalous Hall conductivity. And actually, Weyl point, I said they are monopole of this omega field in 3D. And if we do this integration, actually, for monopole, it's really easy, because between two monopole, we put a two-dimensional plane. The flux from the positive monopole to the negative is the integer. Then this is the integer. That means this actually if we only look at the one plane, it's a quantum Hall plane. We have an integer chain number. And then when we move this plane, if between these 2 points, we always get a quantum Hall. And we move it out, we get 0, exactly 0. Then therefore, the total enormous Hall conductivity, just the distance of these 2 Weyl points. If it's separate long, we get a larger value. If it's small, we get a smaller value. Then it's represented in this way. Yeah, we know to measure an enormous Hall effect, or Hall effect anyway, it assumes we break timers of symmetry. And at the beginning, well, suppose we have Weyl semimetal, we expect some Hall effect. But at the beginning, the first Weyl semimetal were discovered, like in this tantalum arsenide family, several materials have same structure, almost the same band structure. And the tungsten ditelluride and molybdenum ditelluride, they're non-magnetic. And the reason is simply like in the band structure language, there are 4 Weyl points. We have 2 give you somehow Hall effect. We have another 2 opposite. In total, we get 0. And time also make the cancellation. And yeah, for quite a while, we didn't have a magnetic Weyl semimetal. And I work with the materials. Okay, actually, here, this way may give us a clue to look for next magnetic Weyl semimetal. And look for if we know material have some Hall effect, anomalous Hall effect. Possibly, maybe it's a candidate. And at least, practically, calculate the band structure is fast. But find which material to start, that's always a question. And luckily, at that time, I worked with Claudia Fetzer and Stuart Parking. At that time, we started a family of material called magnesium-3 germanium. At the same time, Tokyo group married another material. This is a very interesting non-collinear AFM structure. Actually, surprisingly, this is the AFM material, but it has very strong anomalous Hall effect. Usually, we think about anomalous Hall, we assume, okay, classically mirror a magnetic metal. F magnetic means ferromagnetic. That's what we assume. Most AFM, because spin up and down, this configuration, if they are anomalous Hall, it's cancelled out. These 2 spin channels cancel out. But if the spin structure is non-collinear, we don't have this up-down way. We have this triangle way. And actually, this triangle way, here, the symmetry is low enough. It allows the anomalous Hall come out. This material, these 2 materials, actually, they have very strong anomalous Hall, even to super high temperature. You see, it's 400 Kelvin. And because if you go even higher, the material just gets melt. And then there's a very robust anomalous Hall effect. But at the same time, this motivated me. Why not look at the band structure again? And whether there are Weyl points. Indeed, we find a lot of Weyl points. And in the band structure, actually, the material itself is a metal. No, I talk about a Weyl semimetal, but actually, in reality, this material, band structure is a metal, has a huge electron hole pockets, but near the frame energy, actually, there are many Weyl points. The problem might be there are too many, and it's too complicated. And I don't want to go to the details with you about this 10, 20 Weyl points. And simply like this is a Fermi arc, and this Fermi arc later was verified by this Tokyo group. And I want to, let's come back to this formula again. As I said, Weyl points separate more, we get a larger effect. And it's kind of not quantized, but nearly quantized in the fractional size of the Brillouin zone. And then this value, how big this value? E squared over h, this is the quantum conductance. We know what it is. And in 3D, we talk about conductivity, which is divided by the thickness. This is A is the z direction, the unit cell. And A, we took a value about 5 angstrom. Then this value actually is about 800. But for quite a time, when we mention about anomalous Hall conductivity, it's usually very small. We know for iron, it's 10 or something like that. That's for quite a time. And for this material, Mn13 germanium, their order is 100, 300. 300 is maximum. Not much. Since first I said there are many Weyl points. These Weyl points, they should contribute something, sum it up, right? But this value is still quite small. And maybe we naively go ahead to think, continue this picture, this Weyl point picture, their separation contributes some Hall. and whether it can give us some inspiration. Like we start with the band structure. This is the band structure. I just overlap the valence parabolic and the conduction parabolic. After the cross, suppose there's no spin of the coupling. I have some mirror plane. Actually, in this plane, we will have a nodal line, as Tito said. And then this nodal line, but if we turn on some perturbation like a spin orbital coupling, and we put the magnetic axis from top to the bottom, and we will gap this line completely. But there will be two Weyl points survive. Without think too much, the distance tell us the size of the Hall effect, right? Now let's think a little further. Let's push the band structure slightly. Let's make the ring larger and larger. And then make it larger, then we get more separation. There's an extreme case. Okay, we push the Weyl point to the boundary. We know this is the periodic boundary condition. This Weyl point will meet of the opposite one of next Brillouin zone. When they meet, actually, it's still crossing, but it's not stable anymore. Let's push further. And here, we already get a quantized value, right? Let's push further. We push even further. Okay, we just get a gap. We get a stable gap. We get a gapped 3D insulator, and then the whole connectivity is quantized. Quantized means quantized in a three-dimensional way. And here, it gave us some hint. Like if we start with some huge nodal ring in the Brillouin zone, even the nodal ring much larger than the Brillouin zone, and the consequence might be we will get a big Hall effect. In other way, this is one big nodal ring. Second, if we have many rings, as much as possible, and we sum it up, they not necessarily cancel each other. And then, as a material scientist, I usually ask, okay, what material has this property? As we started, nodal ring is protected by usually related with the mirror symmetry. If we have mirror plane, or if we have many mirror plane, and this can be an advantage. Or in other words, like it means we need large ring and many rings, then we need many mirror planes. And what kind of crystal has many mirror planes? Usually this kind of perfect cubic material or hexagonal. They have a very high number of space group. And when I think about this, actually, when I look many materials we know today we discovered actually already many Weyl semimetals, including this one, Weyl material, nodal line material, they are magnetic. Actually, most of them here, they are ferromagnetic. And for example, one material I pointed out here is cobalt-2, magnesium, aluminum. There's a similar one is gallium. They have huge enormous Hall connectivity. Their order is in like 1,500. This is twice of this quantized connectivity. By the way, these are metals. They are metals. I see quantized, we assume a gap. But if we have other trivial bands across the Fermi edge, it does not harm, right? And then we have trivial states, they cross the Fermi surface, but there are some gapped states actually really contribute to this enormous Hall. Go to the band structure, these colors is this crazy number of nodal rings. And actually, the dominant contribution is from the largest one. And this is just a short story about we use these nodal rings to really enhance quantitatively the anomalous Hall effect. And now next, let's go to the second term, visit this term. For the anomalous Hall, let's revisit, is equal to we integrate all the barrier curvature in momentum space. Also, we know it needs to break the time Russell symmetry. This is usually the experiment setup. You measure Hall voltage is proportional to the current you pass through. For the second order, what happened? Actually, the second order is, first we see the experiment. You will measure Hall voltage has a parabolic dependence to the current. In other words, that means you pass a current, you reverse the current direction, but your Hall voltage does not change. You get the same voltage. And this is qualitatively different from this linear part. And for the nonlinear Hall, we write with the barrier curvature. Actually, at the point Liang Fu pointed out, actually, it's related not directly to the barrier curvature, related to the gradients of the barrier curvature. And then also sometimes we call it barrier curvature dipole. By symmetry, it's very different. Omega itself it's odd by time reversal symmetry. We reverse momentum, we reverse the sign of omega. But the omega and k, these gradients, you know clearly, we reverse momentum is preserve the sign. That means this effect survive with the time reversal symmetry. In other words, we start with a non-magnetic material. There's no magnetism, no external magnetic field. You do a whole experiment. And possibly you will see this second order effect. And then time reversal completely rule out this possibility. Okay, then how this related with the Weyl point? Possibly here, you can see it even clear, like this Barry dipole term, omega is not necessarily too big, but its gradients, like for example, to the Weyl point. The Weyl point give you huge gradients. And then this gradients, okay, in other words, like this is omega is anti-symmetric, and about omega gradients is always symmetric. That means you have left hand, right hand, two opposite Weyl point. They don't cancel each other. And even you have more, they not necessarily cancel each other. And physically, how do we intuitively understand what's happening? We start with a band structure which has time reversal symmetry, but we measure something like a Hall effect. We know this Hall effect, in some sense, always we need to break the time reversal, not by magnetic field, not by magnetic moment. And then actually what's happening is, because this is second order, suppose we start with a band structure, we apply electric field, there's a current flow. The Fermi surface will shift. Yeah. As you see that this non-equilibrium Fermi surface, it breaks time reversal, or in this way. In this way here, the time reversal is breaking. In this non-equilibrium Fermi surface, the left side and the positive side, they're not necessarily same. They have different occupation. Then when you pick up the Barry curvature, you get a non-zero value. And then now we use this toy model. Let's observe. Let's just quantitatively estimate how big this quantity is. And then I start with this Weyl semimetal model. And yeah, you see this tilt term was added by Alexei and his collaborators. And then here, actually this point, okay, we start with this simple Hamiltonian. We can get the omega analytically. And then just like it's a monopole shape. And then its gradients we can also calculate analytically, right? Without go to detail, but the important is actually omega is not related with this tilting. In other words, that means actually this tilting don't change the topology. It's a robust monopole. Then here, actually, that means then I plot this dipole dxy. I plot it here. But what makes a difference? You see, if we put the Fermi surface across some bands, and the big difference is the shape of the Fermi surface are different. Here, the shape is perfectly symmetric. And then here, we start to change. But here, we change dramatically, right? And this change, as I said, we sum over the red color and the blue color. Is this dipole is equivalent to the nonlinear effect. Actually, here, the effect is zero, because red and blue, they cancel. And here, they don't cancel each other, but here, we get a lot of net value. In other words, tilt really has an advantage. Tilt, although sounds like it's complicated, but actually this is a really advantage in real material. Tilt make it even stronger. And then we go to real material, or in other words, this is a molybdenum ditelluride in the band structure. This is the, it's not too clear. This is the Barry curvature distribution. These are two monopoles. Well, you see, I always use this one-year center evolution method. And then what we do next step, just we on a very high dense grade, we calculate the omega. By the finite difference, we can get the gradients with the omega. That is technically we do. And you see here, a lot of huge contribution is mainly related with this Weyl point region. And all the others, like actually we calculate several Weyl material at that time, tantalum arsenide to this molybdenum telluride, tungsten ditelluride. And also, yeah, the same time Evo calculate this pure tellurium metal. And here, in theory, we all find this value of this nonlinear effect. That means if you fine-tune the Fermi energy to the right band structure, or close enough to the Weyl point, we will have this second order effect. although this was never reported in experiment. And then just in last year, actually, this was observed in constant ditelluride thin layer, and like this is the experiment setup in this thin layer by gate tuning the Fermi energy. This gives some advantage to really reach the high value. And you see here, this is the Hall voltage, and this is the current go through. You see this beautiful parabolic relation. And actually, this parabolic can also go down. The direction is controlled by the inside of the material. Actually, is the material inside the electric field, the dipole field, combined with the spin of the coupling. How much time do you have?
Actually, 5 minutes at least.
Oh, okay, maybe enough. Generalize later, like this is a kind of DC limit effect, DC limit second order response. Yeah. And about this nonlinear response or second order, actually more familiar phenomena is called bulk photovoltaic effect. Or for example, the second harmonic generation. It was talked in some talks in this workshop. And in general, like we know if we shine a light to a system, immediately it will generate a polarization. This is the textbook language. This is the linear response. Tell us how you shine a light. It get reflected, get bended. And then this is the second order. This is exactly the second harmonic part. And if we know the current, we can write as the time derivative of the polarization. We get a first term, second term, we can write many. But clearly, the first term, by the average with the cosine omega t, we get 0. But surprise, the second term just come out. And that means, in general, actually, we shine a light to a single phase material, not a cell-cell p-n junction. And actually, there's a possibility we can collect out a DC current. And then to describe this phenomena, actually, like in the last is like 3 or 5 decades, and people developed a lot of deep understanding, for example, the shift current theory, injection current theory. And at that point, people already get understanding. This phenomena, this sigma 2 or chi 2, is closely related with the barrier phase in the band structure. And then when Weyl semimetal was discovered, actually, for example, tantalum arsenide was discovered in 2015. In the second year immediately, Berkeley experiment measured tantalum arsenide for second harmonic effect. The second harmonic coefficient, actually, compared to the conventional material, is in the order of like 100 times stronger. And later, also, there are beautiful theory proposal about there's a quantized response from the single Weyl point. Then what I'm motivated, I'm motivated more about the real material. Okay, in this material, for example, this one, and quantitatively, we use the non-interacting band structure. Since this band structure works well, we compare to APAS. And from the band structure response, we develop a numerical method to understand the material. And when we work on it, actually, this is this might be the first paper pointed out. If we start with a clean band structure, and this band structure in the light field, it will generate a DC field. And there actually the shift current concept was first proposed there. Later was developed by many different theory. Until today, I think the theory understanding is almost complete. Complete in the sense if you derive the second order response, that's a standard textbook second order. This is all the phase diagram we have. And then current understanding is we have shift current in a clean limit. It represents the electron absorb a light. It go from the valence band to conduction band, right? But if we look at the wave function center in the real space, the wave function center will have a shift in real space. This shift will generate a coherent current out. And then the injection current is a different way. Injection current is when you shine a light, if the material is clean enough, actually the photocurrent just keep increasing. Its amplitude keep increasing, go to some upper boundary limited by the lifetime. But when I started learn this literature, I figured out, actually surprised, although this method was developed, but most of this method was applied to study time Russell symmetric material, or they are non-magnetic material. We know if we constrain time Russell to the system, the response function, its shape will be very different. Then I try to ask a question. Oh, maybe is there something more general theory? I work with currently I share this Tobias my postdoc with Adi Stern. We ask, oh, if we break time reversal, we make the system magnetic. Something can happen. Something is missing in this diagram. Well, after we go through it, actually, this diagram is still there, but something different is. For example, if material is not magnetic, we shine a linear polarized light. We only have shift current. We don't have this injection one. And injection only happens when we shine the circular polarized light. But if we start with the system magnetic, and then actually magnetic, like will mix the shift and the injection current, both will exist. And also there are many other different contributions. We give some physical meaning about this process. For example, we know it's related with the barrier phase, the barrier curvature, actually. And then here, I ask question, okay, sounds like everything related with the topology. But with barrier curvature is the only contribution, or there can be something more. And well, simply to think is the diabatic one, simply like the absorption one. And there's actually here, we figure out there's a new term called quantum metric. I think Titus must know it. And yeah, we learned this name actually from some of your papers. And then this part, we usually talk about a quantum geometry phase. Then after that, we see barrier curvature. Actually, quantum geometry phase has two parts. There's a real part and imaginary part. Barrier curvature is the imaginary part. Quantum metric is the real part. For barrier curvature has a very good semi-classical picture. It means the anomalous velocity, yeah, like a magnetic field. But the quantum metric, in physics, what does it mean? Actually, not too clear. There's a pioneering work try to find out in some system maybe this term has a strong contribution. Here we add a little more, means like in this nonlinear effect, especially the shift current, we have this quantum metric contribution. Well, I don't want to bring you to the details of the phase diagram of this thing. Actually, after we get roughly the theory understanding, I talked to Tobias. Well, I see. First, this formula, I cannot do it. Only this is the best poster, do something you cannot do. But I want to get something even simple. Let's see, is there some simple thing can happen or something missing, like we can explain it even to undergraduate students? Oh, that means can explain to me. And indeed, we find something. Actually, this is something like, let's see. Let's forget all this language, complete language or diagram. If we ask an undergraduate student, we shine light to an insulator, what happened? Okay, the light will get absorption if the frequency match, right? We get electron and a hole. From the band structure, we learned the electron and the hole will have opposite group velocity. They just start to travel. In the lifetime, this is a DC current. But however, such current never observed. 1 minute. And the reason also simple, because here you have excitation, here you have another one. They cancel each other. Two current cancel. This is trivial. And then the question comes, since this comes related with this canceling, K minus K canceling, then let's think some way to avoid the canceling. Yeah. And if we break inversion symmetry, we know this kind of rush bar splitting, the K minus K is still symmetric, the velocity is still opposite. And because of time reversal symmetry, then let's go further. Let's break time reversal to break both. And here in this case, you see left and right, they are not symmetric. Well, most of the time when we calculate the band structure, we see a band structure. In the literature, we only see half. We assume the next half are same. But if the symmetry is low enough, especially break P and T, actually they are different. They are slightly different. And in this case, I believe there will be a current come out. But in this case, the symmetry is low. Actually, we also have barrier curvature contribution. And in theory, when we propose something, we want to propose something clean and make it cleaner. Okay, if you measure something, it's purely this effect, and not the known shift current. And then we imagine a phase, like we break P and T, but we have combined symmetry P and T. In this case, we have double degeneracy of every band, but left and right, they are not necessarily same. And then in this case, because of this double degeneracy, PT exclude the barrier curvature. Barrier curvature is 0 everywhere. And in this case, if there's some current measurable, And then we will have this. Actually, this is the diabetic contribution. It's in the diagram. Actually, is this part. And actually, the others. From this picture, we know if we measure current, this current is proportional to the relaxation time, sure, to the velocity difference between the valence and conduction band, and proportional to the dipole transition rate. Yeah, this is the absorption. And we should integrate out in all the momentum speeds. We propose a system, like actually, it's very simple. If we have two magnetic layers, but between layers, they ordered AF and V. In this case, we break time reversal because it's magnetic. We break inversion because two layers has opposite spin. In other words, spin break inversion, crystal has inversion. And actually here, by calculation, such kind of band structure, we get a huge value. And this is the detail of the band structure. You can see this K minus K, you see this small gap, they're slightly different. And this difference break the symmetry of the left and right. And then quantitatively, we may ask another question. Okay, this asymmetry, if it's like we break the symmetry more, we may have higher current, but in what kind of material break it more? And then actually, what we learned is you see these two gaps. They are spin orbital coupling gap. And this is the Fermi surface, not Fermi surface. It's the isoenergy surface defined by the omega transition. There are three bands. We have these three channels. This is the calculation with the spin of the coupling. This is the current density. Without SOC, actually you see a hexagon shape. It's perfect symmetric. In other words, if SOC is 0, we have kind of SU2 symmetry. And in this case, the photocurrent is 0. But we make SOC larger and larger. We tilt this hexagon to a triangle face more and more. Then we will have a larger case. In addition, the last remark is actually there are many materials, and they are magnetic and breaking inversion, and actually not necessary to have PT. Like, for example, these materials, they are started for quite a time. Actually, before experiment, only measure the second harmonic generation. That time, people have a different interpretation. But actually, I think this current, photocurrent, and the second harmonic, actually, they can go back to the same physical origin. And especially, for example, go back to topology, like many doped magnetic topological insulator and many magnetic wire metal, actually, in many conditions, they satisfy this symmetry requirement. And okay, here, I mainly talk with you about this linear term and the second term and their generation to the photo frequency. Thanks.
So we probably have time for one or two questions. Shulhan, please.
Thanks for the nice talk. You mentioned non-collinear antiferromagnetic material, which is large anomalous Hall conductivity.
Yeah.
So is the magnetic moment of that material exactly 0 or small?
Just there's a tiny moment. That advantage is a tiny moment, but that moment has no correlation with the Hall conductivity. Yeah, it simply is like this triangle break the time reversal combined with the lattice symmetry. Ordinary AFM, you have time reversal with the inversion, for example. Yeah.
But the orbital moment may be larger.
The orbital moment, yeah. The orbital, there's a different one. Anyway, Hall is an orbital effect. Yeah.
Any other question? Well, I have one short question. So when you were discussing this manganese 3, germanium or tin, at some point you mentioned, okay, unfortunately there are too many Weyl points, and then there are plenty of bands crossing the Fermi level.
Yeah.
So it doesn't look anymore like a Weyl semimetal, but more like an ordinary magnetic metal.
Yes.
So where would you draw a legitimate border between what you can call Weyl semimetal and just magnetic metal?
Does not make much sense. Whatever. Now today people call everything topological. This is the carrier density of this thing. Actually, that one is a metal, has a lot of carrier. That brings an advantage. When you measure Hall, the Lorentz force, the trivial Hall signal, is inverse to the carrier density. If you have huge density, actually the ordinary Hall effect just go out. And you see the 99% is anomalous Hall signal. Yeah.
Okay, thank you. If there are no more questions, let's thank Binghai
Thanks.
once again.